All right, thanks. I'd like to thank the organizers for giving me the opportunity to talk to you today, and especially a big thanks to my amazing team of collaborators with a very wide-ranging variety of expertise that we brought together for this project. So somewhere around the middle of main sequence lifetimes, rotation and stellar activity appear to decouple, and this may actually kick in before the age of the sun, so it could be relevant to our understanding of our own solar system, in fact. So what I'd like to share with you today is the most direct evidence yet of what causes this change in the relationship between rotation and activity beyond middle age, and in particular that a shift in magnetic morphology is what's responsible. So the big picture here is that we are trying to bring together all of the measurements that are required to quantify the magnetic braking torque in sun-like stars, and effectively, equivalently, the rate of angular momentum loss. So that wind braking torque, following the formulation laid out by Finley and Matt in 2017 and 2018, it depends on the morphology of the magnetic field, so here parameterized by the polar strength of a dipole, a quadrupole, or an octopole field. So it's only the largest scale components that really matter. The mass loss rate, the rotation period, and then the global stellar properties, the mass and the radius. And so we get the rotation period and the mean activity level from archival calcium H and K data from the Mount Wilson Observatory. We combine that with asteroseismology from TESS to get the global properties, the mass, the radius, the age. We fold in measurements in the X-ray from Chandra, also with the ROSAT, to quantify the X-ray flux for our targets, from which you can estimate the mass loss rates. I'll show that a little bit later. And then finally, ground-based spectropolarimetry from the Large Binocular Telescope to either measure or set limits on the strength of these various large-scale components of the magnetic field. Okay. So the big picture here that was motivated by observations from the Mount Wilson Observatory of rotation and activity cycles in solar analogs, and in particular, this sequence of solar analogs, 18 SCO around 4 gigayears, alpha Centauri about 5.5, and 16 Sig around 7, seem to show that after standard spin down, where activity cycles are gradually getting longer as the rotation period slows, once stars hit a critical rotation rate for a given mass, rotation seems to stop evolving, and the activity cycle apparently grows longer and weaker until it disappears entirely in the case of 16 Sig. Now, looking at similar pairs of stars that have comparable rotation periods but have different activity levels, we see similar kind of behavior in both hotter and cooler stars. And so our objective here is a first test of what might be different between a star that is clearly before the transition, like 88 Leo, and a star that is clearly after the transition, in this case, Rho Corbohr, which is our main target here. So we get the astroseismic properties from TESS. TESS observed Rho Corbohr in sectors 24 and 25 and allowed us to get a low signal to noise detection of solar-like oscillations. You can see an excess of power in the Fourier spectrum around 1800 microhertz. When we autocorrelate that range of frequencies there with itself, we get a peak that shows a characteristic frequency spacing that's similar to, in red there, that is similar to the predicted values based on the temperature and other properties of the star, shown as a blue line. And as additional check, we make an Echelle diagram of this region of the power spectrum to see where oscillation modes with the same geometry line up in ridges, vertical ridges here. And as a sanity check, we wanted to see that the ridge of dipole modes has a frequency offset that is consistent with what is expected from solar light oscillations, and indeed it is. So we believe we have a secure detection of the global oscillation properties in this star. So we did grid-based modeling to get the radius, the mass, and the age. For 88 Leo, unfortunately, there was only one sector of observations in cycle 2. And so we were unable to get an asteroseismic detection. So in the case of 88 Leo, we are estimating the radius from SED modeling. We use that with an empirical eclipsing binary mass-radius relation to derive a mass. And then we get the age through gyrochronology from rotation, since it is before the critical rotation rate where rotation and activity decouple. Gyrochronology should provide a reliable age for that younger star. Okay. Now, to get the mass loss rate, mass loss rates are notoriously difficult to directly measure in stars. And so this plot from Brian Wood and collaborators just earlier this year shows essentially all the measurements of different types that can place limits on the mass loss rates. And fortunately, the mass loss rate appears to be correlated with the X-ray flux. And so you can use this correlation to predict for 88 Leo and for Rho Cor Bor what is the mass loss rate that you expect given this empirical relation. And so we get a contrast between the two of a factor of 5. So the mass loss rate decreases by a factor of 5 between the age of 88 Leo, or between the flux of 88 Leo and the flux of Rho Cor Bor. Now, there is a lot of scatter in this empirical relation. The previous relation of Wood and collaborators in 2018 is a bit steeper, fit only to GK dwarfs. It's less scatter in that relation, but it's also applicable over a narrower range of X-ray fluxes. But fortunately, that range encompasses both 88 Leo and Rho Cor Bor. So if we use that alternative power law, you get this these estimates of the mass loss rate. And so that's a factor of 17 decrease. But to be more conservative, we adopted the smaller difference in mass loss rates for subsequent analysis. Okay. Oh, I should mention that the X-ray fluxes that we got here for Rho Cor Bor, we got a new measurement from Chandra of the X-ray flux, and we updated the old measurement from ROSAT of 88 Leo, considering the newly derived distance from Gaia and updated determination of its radius. Okay, so the Large Binocular Telescope gives us measurements and limits on the magnetic morphology. These observations were obtained in 2019. So this shows the degree of circular polarization across the line profile. And what you see is a signature of a dipole magnetic field in 88 Leo, a very clear detection. Keep in mind that we're looking at 1 part in 10,000 is the full scale here. So these are tiny degrees of polarization. It's hard, these are hard measurements to make. But for 88 Leo, we derive a dipole field with a strength around 5 Gauss. While for Rho Cor Bor, there's no significant detection, but we can use the little blip around the line center to set upper limits by assuming either dipole or quadrupole or octupole field. Now, we know the relative activity levels of these two stars based on their chromospheric long-term measurements of their chromospheric activity levels. And so we know Rho Cor Bor is 64% as active as 88 Leo. So if you just scaled down that 5 Gauss dipole field, you would expect to detect in Rho Cor Bor a 3.2 Gauss dipole field, if nothing else changed, for example, the geometry. In fact, we set an upper limit on the dipole field of 0.7 Gauss. If it's a quadrupole field, then you have patches of opposite polarity that cancel each other out. And so the amplitude of the field can be larger for a given line profile variation. And so the upper limit of a pure quadrupole field is 2.4 Gauss. That's still not at the 3.2 Gauss that we'd expect from the relative activity levels. If it's octopole field, there's plenty of room to squeeze an octopole field in there. And given these upper limits, we can say that the global field of Rho-Core Bohr is likely to be dominated by quadrupole and higher order fields. Okay. All right. So what did we find when we put all of these things together? The first point is that the asteroseismic age that we derive from TESS photometry for Rho-Core Bohr is perfectly consistent with the mean activity level expected for that age from a sample of solar analogs. So in the background here is the activity age relation for a sample of solar analogs from Lorenzo Oliveira and collaborators in 2018. And you can see this is the gyro age for 88 Leo, the asteroseismic age for Rho-Core Bohr, and they fall reasonably close to that activity age relation. If instead you adopt the gyrochronology age for Rho-Core Bohr, it's a significant outlier. So the asteroseismic age is perfectly consistent while the gyro age is not. So with that as motivation, we tried to model the forward model the rotation period of Rho-Core Bohr using either standard spin down, a standard spin down law, or weakened magnetic braking, where you essentially turn off magnetic braking around the middle of main sequence lifetimes. So for standard braking, you would expect Rho-Core Bohr to have a rotation period around 50 days. With weakened braking, you can push that down below 30 days and just barely get to the observed period shown here in black. Now, this led us to suspect that the low signal to noise detection in our asteroseismic study may be slightly biased. In fact, there is a bit of a tension between the observed, the asteroseismic mass that we derived and the mass from isochrones and other analyses. If you use an alternate mass prior instead of the asteroseismic mass, so based on, say, isochrones or the eclipsing binary relations, you can push that predicted rotation period with weakened magnetic braking down to be consistent with the observations. So by contrast with 88 Leo, standard spin down models can perfectly match the observed rotation rate as expected. So, but for Rho-Core Bohr, weakened braking models are required. So now we basically have all of the ingredients that we needed, as I showed in the beginning, to predict what is the magnetic braking torque for each of these stars and how do they compare. And so when you just plug in all of those ingredients, what we find is that the magnetic braking torque for Rho-Core Bohr is more than an order of magnitude smaller than it is for 88 Leo. And just to put that into context, there are a number of stellar properties that will naturally lead to a decrease in the magnetic braking torque. For example, the natural evolutionary decrease in the wind mass loss rate, right? And also the gradual slowing of rotation, maybe just by expansion on the main sequence if there's weakened magnetic braking, and also the gradual decline of the stellar activity level, the mean activity level. All of those things will produce a reduction in the magnetic braking torque. And so those expected things can account for a reduction of about a factor of 3 between the age of Rho-Core Bohr, or the age of 88 Leo and Rho-Core Bohr. To get that extra factor of 4 on top of that, that comes from the shift in magnetic morphology. So effectively, the elimination of the dipole magnetic field and the concentration of the field into smaller spatial scales like quadrupole and above. Okay, so we have new LBT spectropolarimetry for another 5 solar analogs that we expect to be able to apply this same methodology to in the near future. And we have 4 additional cooler targets planned. So we're planning to test this scenario across the full range of spectral types. TESS is going to observe in cycle 4 most of our targets in a 20-second cadence, and thanks to a DDT proposal for that in part. The one target that it will not observe that we're interested in is 18 SCO. That's a victim of the northward shift of due to scattered light in cycle 2 and again in cycle 4. So I'm looking forward to cycle 6 to finally observe 18 SCO. But in the meantime, we have ground-based asteroseismology of 18 SCO. But with those 20-second observations, we expect we can improve the signal to noise for rho core Bohr, the astroseismic detection, and hopefully get a detection, an astroseismic detection in 88 Leo to confirm this general picture. So I'll just leave up my summary of conclusions and encourage you to read the paper that was posted on arXiv last night to get the full details. All right, and I'll take any questions.